Good morning, students. Today class we are going to discussing about the joint density function. Already we know that the joint distribution function we are writing is a capital of x comma y of x comma y. The probability of it's a joint event we are having some discussion about that. Here we can able to defining the joint density function. Already we know that the joint density function is and the relation with joint distribution function. In previous sections, we can hang that the relation between density and distribution. Density and distribution. The relation between density and distribution is the density function is f(x) of x is equal to the derivation of its distribution function. Its distribution function. We can writing like here. Distribution function, that is small f(x) of x is equal to d by dx capital f(x) of x, f(x) of x. Here you can calling it is a joint density function. Already the name is indicating joint. Here you can hang this joint term. You can calling it is a common between any two random variables. Let us consider two random variables x comma y, its joint density function. You are defining with the second derivative. It is a second derivative of its joint distribution function. First of all, we have to give the notation of joint density function is small f(x) comma y of x comma y. X comma y. This function we are writing the second derivative. The second derivative here you can writing this second derivative is a partial fractions. Is a partial fractions, that's you can writing dou square divided by dou x dou y into its joint distribution is f(x) comma y of x comma y. This one is called the joint density function. Joint density function formula. You can writing when out to taking that x and y, the random variable x and y both are discrete. The density function we are writing small f(x) comma y of x comma y is equal to, and taking the summation m is equal to 1 to n and summation m is equal to 1 to n. Here you can writing the joint probability. It's a probability of xm comma ym into del of, you can writing as a x minus xm or x minus m into del of y minus m. This is a formula for when the two random variables are discrete. The joint density function formula is summation of m is equal to 1 to n and summation m is equal to 1 to n into its joint probability function is multiplying with its impulse values. The impulse value of x and the impulse value of y. This is a formula for that. By using this formula, you can able to find its joint density function. Joint density function, it is having some properties. The properties of joint density function. The first property. Already we know that the fundamental properties in a density function is, the first property is small f(x) of x is greater than or equal to 0. And the second essential property in a density function is integral minus infinite to plus infinite f(x) of x into dx is equal to 1. These two are the essential properties in a density function when you have to consider single random variable. Suppose you need to consider interval. The interval is probability of x1 less than capital X less than or equal to x2, less than or equal to x2. This one you can writing with integral. The limits are x1 to x2, x1 to x2. The density function is fx of x into dx, x of x into dx. This is a formula for one how to consider the single random variable. Here also you can consider the joint density function. The same formulas can be reflected here. You can see the first formula. What is the first one? The first one is small fx of x is greater than or equal to 0. The same thing it can be repeated here, but you can additionally representing it's one more random variable, that is a joint density function, that is fx comma y of x comma y. Fx comma y of x comma y, the value is greater than or equal to 0. The value is greater than or equal to 0. The next property is you can consider the interval value in between minus infinite to plus infinite. The value is a 1. The value is a 1. But here we can take in the additionally one more integration. It is relating to the another random variable of y. That's why I'm writing the second formula. The second property of a joint density function is integral minus infinite to plus infinite and integral minus infinite to plus infinite. The joint density function is fx comma y of x comma y. The integration is done with respect to x and with respect to y. The total value goes to 1. But you can see here the main difference of these two formulas. Here you can using the single random variable, you can write in the formula like this. Here you can increase in the one more random variable, that's why you can represent the one more integration term, and it's a joint density function, and you can also representing its respective value of y. The complete value is equal to 1. These two are the essential properties. Of joint density function. Here you can remember, here I am calling the joint density. When you call in the joint density, when the random variables is having a common portion you can call it a joint. Here I am saying that the joint density function value under a interval, the value is equal to 1. Otherwise, the area under joint density function is equal to 1. These two are essential properties when out to checking that the given density function or a given joint density function is a valid or not. You can check it by using these two conditions. One is a greater than or equal to 0, and second one is this one. Coming to the next one, interval. We can consider the interval. The interval is probability of x1 less than x less than or equal to x2, comma y1 less than y less than or equal to y2. This one you can writing with double integration. Why? We are having the two random variables. That's you can writing with the double integration. The first integration limits are x1 to x2, and second integration limits are y1 to y2, and you can writing the joint density function is fx comma y of x comma y dx into dy. This is a formula, but here we are having that is a proof of these properties. We will not do for that. Already we are having some derivation part for these properties in a last sessions. That's why we are not taking that any more derivation part. Just you can remember that what are the formulas and what is the main difference between a single random variable and two random variable case functions. The next one is marginal. It's a marginal density functions. Already we know that the definition of marginal function. What is a marginal function? The marginal function, we are defining that we can obtaining one random variable, we are setting another random variable is a infinite. We are obtaining one random variable, we are setting the another random variable is infinite, is calling marginal function. Here you can calling is a marginal density function. Marginal density function. First of all, you can writing that the notation of joint density function fx comma y of x comma y. X comma y. In this function, how many random variables we are having? We are having the two random variables x and y. X and y. First of all, I'm obtaining the random variable x. I will make that the random variable y is infinite. The random variable y is infinite. For this fx comma y, the first one is a normal and second one is a infinite. Second one is a infinite. For this function, I am writing its integration. This entire value is equal to fx of x. Fx of x. We can obtain the x value, we can making the y value is infinite. The process is calling the marginal density function of random variable x. The formula for this marginal density function of random variable x is integral. Here we are having the formula of this one. In this formula, we are just neglecting the one value. We can take in the double integration of this quantity. The double integration quantities are one value is assigning to infinite, minus infinite to plus infinite. What are the value we are obtaining that? The value can assign to limits is a minus infinite to x. Minus infinite to x. Its joint density function fx comma y of x comma y. X comma y into dx and dy. Dx dy. In this case, we are eliminating the y term. We are eliminating the y term with the limits of minus infinite to plus infinite. We are obtaining the x value of the entire function, the limits of minus infinite to x. Minus infinite to x. This is a formula for the marginal density function of random variable x. Random variable x. Similarly, in case of marginal distribution, it's not a marginal distribution, it's a marginal density function for a random variable y. Fx comma y, x position we are filling with infinite and y is a normal value. Y is a normal value. We can make this x value is infinite. We can obtain the random variable y density function. We can calling it is a marginal density function of random variable y. The value you can writing is fi of y. Fi of y. The formula for this is fi of y. Fi of y is equal to the same formula can rewriting here, but the element we are eliminating that is x term. X term we are assigning the limits is a minus infinite to plus infinite. Minus infinite to plus infinite. These limits is belongs to x, and y terms had to assign the limits is a minus infinite to y. Minus infinite to y, and you can rewriting the joint density function is of x comma y of x comma y dx dy. Dx dy. Can remember simply we can obtaining the marginal density function of random variable y. We can setting the random variable x limits are infinite. Limits are infinite. We can able to finding the marginal density function of random variable y. These are the formulas we are having under joint density function. Next, we have to see that some of the example problems. See, one example problem is relating to joint density function. Here is given the one problem is find the value of small a so that the function is a valid density function. The function is a valid density function. Find the marginal density function of x and y. He is giving that is a joint density function. From this joint density function, he is asking the find the small a value. small a value, and can able to find the marginal density function of a x and y. Here is clearly giving that it is a valid density function. It's a valid density function. Already we know that the valid density function equation. Solution of this problem is, you can writing that the given data is a function is of x comma y of x comma y is a x square y. Its limits are 0 less than x less than or equal to 1, and y limits are 0 less than or equal to y less than or equal to 1. 0 for else. 0 for else is a given data. For this, we can able to find the value of a. Value of a. Suppose the given joint density function is a valid density function, we can consider the condition is minus infinite to plus infinite. Here minus infinite to plus infinite. The joint density function of x comma y of x comma y into dx dy is equal to 1. This is the condition for valid density function. Now I am substituting that are the limits is having for a random variable x and random variable y in this relation. The random variable x limits are 0 to 1. 0 to 1. Similarly, the another random variable is also given the same limits of 0 to 1. In some cases, he is given that is different limits. And you can writing the joint function. The joint function is a x square y dx and dy is equal to 1. Now you can applying the integration with respect to x, dx and x limits. You can take this term as a constant, x is a variable, and out of making the integration with respect to x, y is a constant. Y is a constant. That's why I'm writing the y limits is separately 0 to 1. I will apply the integration on x square. For integration of this quantity is x cube by 3 into ay the x limits are 0 to 1 into dy is equal to 1. Now you can substituting these limits. 1 is a higher limit minus lower limit. The quantity of this one is integral 0 to 1 by 3 minus 0 into ay into dy is equal to 1. Okay, the 0 quantity is totally eliminated and remaining is 1 by 3rd into a is constant, 1 by 3rd is a constant. Now we can apply the integration with respect to y for a y variable. We can writing for this, the integration of y is y square by 2, its limits are 0 to 1 into 1 by 3rd a is equal to 1. From this we can substituting these limits is 1 is a higher limit and a 0 is a lower limit. We can substituting these quantities is a 1 by 2 minus 0 by 2 value is a 0 into 1 by 3rd a is equal to 1. The total value is a by 6 is equal to 1. From this a value is equal to 6. When now to gain the function like this, he is saying that it is a valid function. You can use this relation or a property of a joint density function. Then you can easily finding that the unknown parameter in any joint function. This is the first point. Coming to the second one. What's the second point? We can finding the marginal density function of x and y. For this, here I am writing the marginal density function formulas. Marginal density function. already we are writing that you can setting one value is infinite and another one value is a normal, you can obtaining its marginal density function. Now I'm writing the formula for the marginal density function of x. Fx of x is equal to, now I'm setting the infinite, minus infinite to plus infinite, minus infinite to plus infinite. The function is density function. It's a joint density function. Is fx comma y of x comma y into, we can making that integration with respect to y. Why? The entire function must be lying in terms of x. That's why you can neglecting the y term in this joint function. Here you can substitute in the quantity of a value. Now I'm writing that the limits of already y limits is given that. Suppose he is not mentioning any limits of y, you can consider minus infinite to plus infinite. But in this problem is clearly mentioning the limits of random variable y. That's why I'm assigning the limits is 0 to 1. 0 to 1. The function is, the a position I'm replacing with 6. Why? Already I'm finding that a value is 6 into x square y, x square y into dy. Here I'm making that integration with respect to y. That's why you can take that 6 x square is a constant, 6 x square is a constant, and 0 to 1 y into dy. Can performing the integration for a y, the value is 6 x square is a constant, the y integration is y square by 2, y square by 2, the limits are 0 to 1, 0 to 1. You can substituting this higher limit and lower limit, you can writing 6 x square is a 1 by 2 minus 0, 1 by 2 minus 0, the value is the 6 3 times, the 2 1 times, the 3x square, 3x square. This one is the marginal density function of x. Fx of x is equal to 3x square, 3x square. Similarly, you can find that the marginal density function of y is fi of y. Fi of y is equal to, we can eliminating the x term. That's you can set that infinite value is a minus infinite to plus infinite. The function is joint function fx comma y of x comma y into, in this case you need to neglect or you can eliminate the x term. That's why you can make an integration with respect to dx. Now you can substitute the limits is 0 to 1, 0 to 1. The joint density function is 6 into x square y, x square y. Here we are making the integration with respect to x. That's why the y and 6 both are constants. That's why I'm writing 6y is outside to the integration and remaining is 0 to 1, 0 to 1 x square into dx, x square into dx. You can apply the integration on x square. The value is 6y is a constant, it is x cube by 3, its limits are 0 to 1, 0 to 1. Now you can substitute this higher limit and lower limit in this one. You can writing 6y 1 by third minus 0, 1 by third minus 0. Here you can cancel this 2 terms, the 3 2 times, 3 1 times. The value is a 2y. The marginal density function of random variable y is 2y. These are the solutions for a given data. What is given that is given the joint density function. For this joint function is asking find the unknown parameter when the joint function is a valid density function. That's why I can choose this property, can able to simplifying this entire one, can obtain the a value. This procedure is a common for any model problems like this. And second point is we can find that is a marginal density function of a x and y, x and y. Here and the formulas are like this. The marginal density function of random variable x formula is fx of x, fx of x is a minus infinite to plus infinite, fx comma y into x comma y into dy. Just you can eliminating the term of y. In case of marginal distribution, is a marginal density function of a random variable x. Similarly, in case of marginal density function of random variable y, we can write in the formula is we can eliminating the x term in a joint density function by setting the infinite. By setting the infinite, these functions is representing the marginal density of x and marginal density of y.